Well, I think we can get started. Thanks all for coming to the educational workshop on OpenFAST. We're excited to present that today. If you don't know me, I'm Jason Youngman from NREL, and I'll be tag teaming with Emmanuel Brandlard here in the front row. And just to give you a highlight of the schedule for today. So we'll go for 2 hours this morning. We have a lunch break at 12:30. This morning is mostly going to be, more of the overview of capability, dive a bit into the framework and so on, so you understand how OpenFAST is structured. May not fully get through the presentation, what's called overview of the presentation. I think everyone got the GitHub link, hopefully. If you didn't, let me know. Actually, just an update on that. I actually did change my slides a bit. So if anyone downloaded the presentation more than a couple hours ago, you may want to just go recheck that GitHub and download the latest presentation. Otherwise, it's mostly up to date. Anyways, I'll present about until lunch, and we'll have a discussion then. Take a lunch break. After lunch, regardless of where we are in the presentation, we're going to switch over to Emmanuel Brandlard, who's going to do more of the practical, hands-on, give you some exercises and what he calls leveling up. So if you're at this level, how do you get to this level of expertise in OpenFAST? We'll take another break at 3:30, and then I think Emmanuel and I will decide at that point, how we want to wrap up the end. If we want to finish the slides, go through topics that have come up over the day. We'll kind of play that last section by ear as you guys have questions. Does that make sense? I want this to be interactive, so let's start that. I don't want to go everyone around the room introduce themselves. That would take too long. But let me first say who's used OpenFAST before, and instead of raising your hands, let's stand up because let's get some exercise. This room is dead unless you move. So who's used OpenFAST for? Okay, for those standing. Who well, maybe I'll start again. Who's okay? So we got about maybe half OpenFAST users. Sit down now. Who's used tools other than OpenFAST but are similar in nature? Bladed, Hawk2, Flex, Ashes, Qblade. Okay, we got a nice group of those. Now, who would consider themselves basic? I don't know much about this stuff. Maybe I've tried it before. Few people. Who's maybe moderate? I know generally how it works, but I want to get to that next level. Who's at that level? Mostly a few people. Yes, great. And who's who can teach this class? Yeah, thanks, Emmanuel. Okay, well, I saw Rick Damiani signed up, and I was like, why are you signing up for this class? Anyways. Okay, well, great. I'm glad Emmanuel stood up there because he's going to be teaching class. Maybe another question. Who's from academia, like a PhD student, professor? You stand up. Yes, nice. Thank you. Who's, you can sit down. Who's more from a research organization? Yes. Yes, okay, good. Smaller percentage. Who's more from an industry, OEM, consultant, developer? We got a few of those as well. So nice. I think we have a really thanks for making me give you some exercise there. But I think you can kind of see there's a large range of skills, ability, expertise with the tools. I think we're trying to play that middle ground where hopefully everyone will get something. But yeah, I think the goal is to get you to that next level anyways. If you're basic, we'll get you running the code. And if you can already do that, we'll get you to that next level. So anyways, that's the plan for the day. Before I jump into the presentation, I wanted to just do a couple, wind energy 101 items that I think are useful when we start talking about tools like OpenFAST. So I have a question. Open up my so I'm going to propose a very simple thing. We have a rotor that is like an ideal rotor. It has variable speed control. It has, a control system with collective pitch. The yaw always lines itself with a nice uniform wind. So it's always uniform wind. It's steady state, and only can slowly vary over time. So it's like a wind tunnel, but I slowly change the fan speed. So it always follows. the wind. So this is like the ideal situation. Obviously, in the real world, it's not going to be like that, but that's the ideal situation. My question is, first of all, where is the highest thrust load on that rotor? And I have four options here. Is it V in? So when the rotor first cuts in, is that where you're going to see the highest thrust? Again, it's steady state, it's rigid rotor, it's uniform flow. It's always aligned with the wind. Is it rated wind speed? Is that where you're going to hit max thrust? Is it cut out? Or is it the highest wind speed you're ever going to see, the V50, 50-year extreme wind speed? Where's the highest thrust in this rotor? Again, assuming it's a normal control, it feathers away when you shut down. So who thinks it's V in? Stand up, raise your hand. Couple people, yes. Who thinks it's V50? So the 50-year extreme is going to drive the highest thrust. No one. Interesting. Cut out. Anyone? Stand up. Cut out wind speed. Maybe one could do. How about rated wind speed? Okay, most people, yes, and I agree with that. So normally, if you look at thrust, and I'll say this is the thrust curve. Hard to see my mouse here, but I don't. Where's my mouse? Oh well, yeah. So normally thrust would be like squared up to V rated, then it drops, and then once you get to V out, the thrust will. I can't see my mouse again, but where's my mouse? Let's do it this way. Sorry about that. Normally the thrust would drop once you shut down the rotor and then maybe start climbing again. That's normally what it looks like. So steady state, it's interesting, right? The highest wind speed won't drive your load. Now I have another question. Turbulence, turbulence, obviously in real atmosphere, there's turbulence. It's not steady state like this. So standard deviation of wind speed as a function of wind speed. So if I draw, so like say sigma u versus u. Again, I can't see my screen here, unfortunately. So sigma u versus u, what does that look like? Is it going up? Is it going down? Straight? Anyone? It goes down? Is that what you're saying? Or is it going up, buddy? I would say it's not. I would disagree with that. Anyone else? Sigma u. Yeah, now you're going to correct it? Yeah, it's not TI, it's sigma u. So you got to change it or constant. So we have a constant. Anyone else want to guess? See another down, or is it up? I don't know. It's like screen right, left, right? The stage right, left. Anyone? Goes up. I generally agree it goes up, and this is generally like most sites, it actually goes up. And loads. So loads, of course, are going to be some combination thereof of mean things like I showed for thrust. So we have the mean load, and we have the variation. Variation tends to scale with standard deviation, right? So TI actually goes down because you're dividing sigma u by u. That actually goes down. But thrust, the standard deviation generally goes up, and your loads generally go up. And so what you normally see is you basically add that standard deviation on the load curve, and it spreads. Some loads are going up, some are going down. There's some oscillation there. And so if you look at really the extremes, they may not be at rated anymore. They may be at cut out because of, it's not just the means of standard deviation. That's important. Also fatigue, gets more and more important as you get to higher and higher wind speed, and eventually you shut down the turbine, mostly because of fatigue, because your standard deviations are just too high, and you can't, it's not worth the energy you're getting at that point to survive it. So that's one thought exercise I want to give. Any questions on that? Does that make sense? Yeah. That's a great point. There's definitely a subtlety there, and I agree. I'm thinking like the higher tier of the standard deviation, right? So maybe I should clarify that's what's really driving loads. No, I agree that's true. So I simplified that. Maybe another thought exercise here. Another thing I always like to think through is a spring mass damper. So I'll draw it here. Sorry, this is like, I can't even draw this thing, but there's a spring, there's a damper, there's a force applied, and a displacement. And so I want to say, first of all, what's the equation of motion of a mass spring damper system? Anyone? Mechanics 101, yeah. Yeah, sorry, I can't draw with this thing, but this is testing my ability on a mouse. Plus kx equals f, right? Okay, so there's we know that, and I want to say for this system, what's the difference between a resonance and instability for that mass spring damper system? Instability of that mass spring damper system would look like what? What feature of the model would be an instability? Yeah. Yeah, so that C term, that damping is negative. That's an instability. What's a resonance for this model? Right, so you take your natural frequency, which is what, square root of k over m. That's your natural frequency of this mass spring damper. And if your force equals that, basically oscillating at that frequency, you got to get a resonance. And if I plotted, say just have a sinusoidal force coming in, and plotted the difference between a resonance and a natural frequency, what would it look like? What would the curves look like? What's the resonance going to look like? You remember? Going to oscillate, of course. Is it going to grow? Is it going to diminish? Grow? Is it going to grow linearly, exponentially? Exponentially. I would argue against that. I would say it's actually going to grow linearly. So resonance is like a linear growth. But if you go for an unstable system where the damping is negative, as we said, what is that going to look like? Exponential. So these are key things in turbine design. So I think these are the fundamental, wind energy 101. I wanted to make sure is clear because a lot of OpenFAST is around this stuff, right? So loads, I don't care about this B rated. If it's mean, yeah, that's great. But if it's not, I care about standard deviations and I care about kind of the whole span. And as you get to higher wind speed, standard deviation is going up, fatigue is going up, maybe it's driving extremes. And then also in terms of design of the structure, I generally want to avoid resonances. I get this linear growth, generally a bad thing. And I certainly want to completely avoid instabilities. Like that's detrimental. If I get exponential growth, my system's done for. Maybe it reaches some limit state, but these are the kind of things you want to look at. So OpenFAST is really about trying to solve these kind of problems, loads based on wind speeds and other things, avoiding resonances, avoiding instabilities. These are kind of the problems we're trying to solve with OpenFAST. And usually have a whiteboard, it's a lot easier. So sorry about the lack of my ability to do paint there. Let's jump to the presentation. Okay, well, again, you guys should all have this. If you download GitHub, so you can take notes on the side. Again, if you downloaded it a while ago, if you're still have access to the internet, you can download the most recent version. Yeah, let's also make it interactive. There's various pause breaks, obviously, where it naturally makes sense to ask questions. But if you want to be even better, if you interrupt and ask a question, let's make it engaging, not static. Okay. So first of all, if you're here a couple hours ago, Rolf gave a really nice overview of the portfolio of WIDO tools, ranging from the physics tools I'll talk about here, as well as all the cost models and other things. But this is showing just really focused on the physics capability of the tools, and in terms of fidelity on the columns, and then the two applications being like a single turbine performance, focused on the turbine level and then focused on the farm level. And so, today what we're going to talk about is mostly the OpenFAST block, and that's what you sign up for. I just want to make sure you're aware of that tool in the context of the rest of the solvers. We'll touch a little bit on FastFarm today, but I'm actually very curious. If people want workshops on that, that could be something we offer in the future. But focus mostly on OpenFAST. We'll touch a little bit on FastFarm because there's definitely some tie-ins there that are important to understand. And these tools are really about, detailed design. So it's really about, I want to run through a lot of load cases, through all these wind conditions we just talked about, get ultimate loads, get fatigue loads. That's what we're trying to do with tools in this category. If you go to a high fidelity level, these are very computationally expensive. If you're generally doing CFD, you're really trying to resolve as much physics as you can. Generally, for a given project, you can't run too many simulations like that. In OpenFAST and FastFarm, you never run that once. You run that 10,000 times, a million times, depending on what you're trying to do. High fidelity, you're stuck. You're kind of limited to what you can do. So you focus on things that are really, really important. And I try to think of like using those tools to understand what's going on and inform, what we can do at the lower fidelity. There's also a set of even lower fidelity tools that we have in the portfolio, really for design exploration. So these tools, unlike OpenFAST, they don't run, time domain simulations, say in real time. It's really, steady state type things that we can do lots of things really quick. But obviously, you're throwing detail out because we can't solve much physics there. We really understand the design space in that space. So hopefully that gives you some context of the capability. And there's also a tool called WISE that sits there, which I'll talk briefly about in the presentation. That's really our systems engineering and optimization platform. Currently really focused on the turbine level. I think at some point we'll bring that to the farm level. But it's like, how do we do, conceptual design and bring that up to the detailed design phase in a nice, systems engineering optimization approach. And then, of course, in terms of applications of OpenFAST, what we really say OpenFAST is really trying to bring in lots of things leading to a goal. So these are the kind of things going into the model. Of course, we have standards, IEC standards. There's also certification body requirements and so on. So these are basically saying here's the kind of load cases you need to run. And we want to, of course, make the tools applicable to that. Yeah, in the back. Yeah. Wisdom has some quasi-static models. So like you can calculate maybe a mean load because there's no turbulence in it. And maybe it has a dynamic application factor or something to kind of estimate what the real load would be, but it has no dynamics in it. So it doesn't really, does that make sense? So it does do optimization. We are trying to, when we introduced WISE, we had Wisdom and we built on it. And we're trying to say, well, maybe the optimization is really in WISE now, and Wisdom is more a collection of low fidelity, cost, sizing type models, if that makes sense. So the quasi-static models that can use to do some preliminary design. And really the optimization is happening in WISE, I would say, these days. So standards is the one thing. Again, they will kind of dictate the requirements that we have to run simulations for. Obviously, theory is important. Unlike the full computational fluid dynamics, we have to make some approximations of theory, and we can't fully solve NAWEA or Stokes in OpenFAST because we're trying to aim at running up thousands and thousands of times. So there's definitely some approximations to theory there, but obviously the fundamental theories are there. Bringing in technology innovation. So anything, we see some change, this is showing something that we haven't done much with yet, like a partial span pitch. So some new technology comes into play, we want to make sure the tools can represent that technology. And because we have approximated some theories here and there, we bring in two things, really trying to fill in the data needed to do semi-empirical type models and so on. So obviously real test data is often used to sort of calibrate coefficients in the model where we have a high uncertainty, as well as computational solutions. So using these a lot is used as input to the models. Of course, the goal is to do advanced technology. And so, these are a range of things that we, have looked at. Obviously, 3-bladed is standard, looking at 2-bladed rotors. I love that Suhawk in the presentation on Tuesday night really said, I was surprised that 2-bladed didn't make it. Maybe it will someday. So that's definitely something we keep having interested in. Let's see, advanced sensors, LiDAR is looking forward and so on. We want those capabilities now exist in the solve, and can be used for controls, new actuation, smart actuators on your blade or whatever, something we want to, things that are continually looked at. Moving to the farm level, we're talking, how do we do loads analysis at the farm level? How does the wake steering type controller or the helix affect structural loads in your design, not just power? Full plant controllers, and then of course, novel components like drivetrains, towers, and of course, lots of work on floating and fixed systems offshore. So that's sort of the application space that we're looking at. Talk a little bit about, wind turbine design principles. I just want to make sure that, again, fundamental to all that is the need to kind of consider that this system is like, it's like as large as a civil structure. This thing is like the size of a skyscraper in New York City, but it's not just a passive thing that's there. There's a brain, there's a control system in it that we have to consider. There's of course the aerodynamic loads, and so this is I step through this all, but yeah, there's the aerodynamic loads, of course, that are really important. We have to capture that. There's the structural effects. There's the interaction of that aerodynamic or hydrodynamic load with the structure and the dynamics of that structure. Like I mentioned, there's a brain or control system that's interacting there. And as soon as you put that turbine on an offshore platform, you got the motion, you got additional loading from waves and currents and all that stuff. So it's really trying to bring all the things that will sort of drive loading is what we're trying to do in OpenFAST. Again, sort of this design standards sort of set requirements, and I would say loads analysis is very much like customized to the wind application. So if you look at the standard, these are all things that have there's normal operational cases. You kind of sweep the wind speed range and see what happens. There's faults and shutdown events that we know drive certain loadings and fatigue. There's of course once you reach that high wind event, you've shut down your turbine, to avoid all that fatigue with minimal power. You park the rotor or idle the rotor, and there's extreme events that may happen that could drive loading. There's maybe transport assembly installation there. Again, look at that space. For land-based systems, sort of once you've sort of down selected what matters for your turbine, you're probably talking about 1,000 sort of design driving events that may be important. So again, we have to run through all those cases. Offshore, that probably double or order of magnitude bigger. If you look at sort of like straight out, follow all the requirements of standard, you're probably for land-based, it's probably 100,000 simulations. If you down select it, it'll stop 1,000. And offshore, it's probably 1 million simulations. So we really need to that's sort of the core of what we're trying to do is run through all these cases. With two main outputs. One is ultimate loads, as we said. So what's the highest load that the turbine will experience over its lifetime? Normally, we try to do it beyond the lifetime, say the 50-year is sort of the industry standard or what we're targeting. So what's that sort of 50-year maximum that's going to happen? And also fatigue over its lifetime. So those are the two main things we try to use the tools for. And so really that loads calculation, the OpenFAST piece is the key thing for that loads calculation. Of course, you follow that with some sort of limit state. As you'll see with OpenFAST, it's really about beam type models. So you'll get things like shear forces and bending moments, but you won't directly get stress and strain. And so you generally have to follow that up with some detailed structural analysis of the given component. That's called limit state analysis, where you're really checking that stress and strain against its the material capabilities. And assuming all the loads pass those constraints, and they're under the resistance of the material, then your design is good. But obviously there's an iteration that happens in that process. Yeah, and of course that's all IUC. So that's high level again. And the other part is on the turbine response. So in that loads analysis, ultimate loads, I think we've mentioned that it's not just always driven by the highest wind speed or the biggest wave. It may be driven by that, but it may not be, which is quite interesting for wind. So you have to kind of span its operational life to see where that extreme condition is. And also, it may not be one thing that drives the highest load. It may not be one event. One event may drive the blade root bending mode, and something else may drive the tip deflection. Right? It may be completely dependent. So there's a range of things we have to look at. Fatigue, again, it's really about accumulation over its lifetime. And I mentioned those two things in that simple mass spring damper problem, resonances and instabilities. And sort of the first thing we do to analyze those things is generate Campbell diagrams. So these are identifying, the natural frequencies as a function of rotor speed or wind speed, and also the damping ratios as a function of rotor speed and wind speed. Obviously, if there's intersections of natural frequencies with the rotor speed or its harmonics, that's where potential resonances can happen. So anything where I'm showing where the natural frequencies that are crossing over, that's where the resonance is. It's not guaranteed to happen. It depends on how the loads are relative to the motion. If it's orthogonal, maybe it's fine. But those things we have to definitely be very, very careful on and maybe avoid things like that. And then instabilities. If you ever see things like damping going negative, you have to design around that because you can't survive that. Derek Slaughter gave a really nice presentation on Monday on recent capability we're doing. I think maybe we touched on that today as well to improve that ability to generate Campbell diagrams, but it's kind of core. That's a general broad overview. Hopefully, I guess that's a review to most people. I'll just pause there again. Any questions on that before we start digging into OpenFAST? Back again, yeah.
Well,
right. Definitely tends to be. So aerodynamics certainly is a big area. So aerostructural coupling. One sort of core thing that I know we have a research project on at NREL is like load case 6.2 in the standard requires you to do, it's idling, but the rotor's not aligned with the flow because some storm comes through, you lose power, and if you don't have battery backup, you're kind of stuck where you are. And what you happen is even if the blades are, they're feathered to 90s, to like leading edge into the wind generally, but if the wind starts coming from different directions, you can get to very deep stall. You're past the stall curve. Now your lift slope is basically negative. Negative lift slope generally can generally imply some negative damping. As your motion increases, your load's actually going down, and it makes it even worse. You can be controls, maybe driving things. This happens in floating wind a lot. If you're not careful, if your controller is too aggressive, it may consider motion like wind and do the wrong thing and exacerbate the problem. There's also some hydrodynamic examples. There's also operational cases. Flutter is a great classical example of instability. So these are the kind of things we're talking about. Yeah. All right. And like the structural dynamics themselves lead to instability. I think there are situations. I'm trying to think of one. I've certainly seen it before, but I'm trying to remember what that is. Not top of my head, but you want to have a good example of that if you want to answer that question. I've certainly seen it before. I just can't try to remember where. But yeah, Mario, any? Right, but if there's maybe some rotation, I've seen there's some. Right. I would say generally it's yeah. Thanks. Great. Okay, this next section is really about so we won't be talking. Well, I guess this section is on not the framework. So this is more like a high level perspective on OpenFAST. And so yeah, again, what we're trying to do is this aero hydro servoelastic coupling, both land-based and offshore, both fixed and floating. We talked about these already. So, running lots of simulations, that's sort of fundamental. They're all nonlinear time domain simulations. The other part of OpenFAST that's key is that basically at any point in time, you can pause the simulation and export like a linear version of that model. So we basically take all the nonlinearities, we tangent to the curve, we try to linearize that effect and show you what that looks like in a state space form. Really useful if you're trying to do things like resonance checks and stability calculations. If you can linearize the system, you can really understand the system. Controls engineers love linear models, so these linear models are really useful for these types of things. Looking at full system mode shapes and frequencies, also we do linear models. So yeah, so key is OpenFAST does both of those, and we'll talk through how it does that. OpenFAST modules, I won't go through this one because we'll step through the core ones as we go forward. But yeah, there's really modules for different physics, different components, and so on. But it's a very modular structure, and we'll talk through that in great detail. A little bit quickly on Fast Farm. Think of Fast Farm as like the farm version of OpenFAST, and this is a nice animation from Kelsey Schaller. So this is not actually a CFD simulation. That is an OpenFAST. Sorry, that's a Fast Farm simulation running. The idea with Fast Farm is really you basically say every turbine in my farm is an OpenFAST model, but of course. Adds is all the wakes. How does the wake from one turbine propagate and hit the next turbine? Another big part of Fast Farm is supercontrollers. So if you want to have multiple turbines talking to each other, turbine, you over there do something because I want to do something else, or farm level controller. That's what fast farm could do. For offshore systems, we also have mooring connected at the farm level. So if you have two floating turbines connected by a mooring system, like a shared mooring system, you can do that in a fast farm type analysis. But again, it's not CFD. We're not solving Navier-Stokes for everything. It's an engineering model. And so we like OpenFAST, we're trying to maintain efficiency so we can run lots and lots and lots of cases. I think the biggest project so far we've had with Fast Farm involved 120,000 simulations. So this is definitely possible, with these kind of calculations. Okay. So again, OpenFAST is very, very modular. There's a lot of history there. If you know, we used to call the code FAST. And sort of the latest release before we went to this new modular approach was called FAST 7. I won't really talk about that, but in FAST 8, we did basically a full restructure. So this was about 10 years ago now. We said, where we want to be with OpenFAST is much more modular architecture. So we basically designed that architecture is sort of independent of how the physics worked. We laid out, this is where we want to go. And then we basically recoded all of OpenFAST, all of FAST 7 into that new architecture, and we called that FAST 8. And then I think it was about 2017, we said what we're really trying to aim is not just the NREL write code and give it to you guys, but we want this to be a community thing. So we said let's sort of rebrand and say it's not just and also FAST was hard to search. If you search FAST on Google, you're going to get millions of things that are not related to the solvers. So we said, well, let's rebrand. Let's call it OpenFAST. Open meaning like we want a community around FAST. So we made it, again, it's based on FAST 8 with all this modular architecture. We have 20 modules right now. Some of them are actually coming soon in FAST 4. So you haven't recognized those yet. But so the framework, and I'll go through a lot about the framework, but it's really about expanding functionality. So if you look at all the lines of source code of FAST, it's probably a million lines of code there. It's really hard to sink teeth into if it was like a monolithic solve, but it's very modular. So if you want to know about a specific thing, you can quickly find where that is and dive into those set of equations. So it's modularization really makes that possible, and that's really enabled contributions from, of course, a variety of projects funding development, and also not just NREL, but having the community contribute into that. That's what we're aiming for. I would say it's right now like the framework in terms of GitHub and how to do like the mechanics of that community engagement is there, very clear. I think maybe what's not so clear is how to really engage when people have questions. That's more like a case by case thing. But if you are interested in that sort of level of I don't want to just use it, I want to develop it and make it better, I would say start discussing with us what that looks like, and we'll point you in the right direction. But that's definitely where we're trying to go. There's development of lots of them. So the ones I've starred there are ones that I think when Emmanuel gave you the link for OpenFAST in the mass message is at 3.1. So the ones that are starred, you won't see them in there. So those are actually coming in 4.0. But actually development is happening on lots of them. So these are like new ones that are coming out, but there's actually development happening on lots of them. And I can't actually at the end of the presentation, I'll kind of highlight. We'll still probably do this after lunch sometime, but we'll highlight things that have been happening recently, and we'll talk through more like the recent stuff at the end. And then I just want to kind of outline in terms of process. The codes are big. And so, of course, at the center of the analysis, this loads analysis process is OpenFAST with all its modules. And that's all fine. That's generally packaged into one big solver. So there's one executable there doing that solve that has all the modules together. But there's lots of course, data you need to provide to run such a simulation. And these are kind of highlighting some of the main data sets you would need to provide to OpenFAST to make that happen. So first of all, the airfoils is obviously the turbine has a blade, it has airfoils. We're not doing a blade resolve simulation here. That's too expensive. So we represent the airfoil, with lift and drag polars. So airfoil data is key. Wind data is quite important. So you have to say what's the wind condition I'm going to simulate? Is it a steady state thing? Is there a gust case? Is there turbulence? You have to define that, of course, when you run the code. Like airfoil data, there's the equivalent on the hydrodynamic side. There's hydrodynamic data. and we'll talk about it a bit, but there's, chip theory type approaches where you're given drag or added mass coefficients. So those are the kind of things coming in. There's obviously a controller. Generally, controllers tend to be the most secretive part of a turbine in the industry. And so, if you're a student or something, you're probably using a code like Roscoe to generate that. If you're, partnering with some industry client, they're usually not going to give you the controller, so they'll give you some black box TLL. But obviously, if you're in industry doing the work, you probably have your own controller. But so I would say in terms of controllers, OpenFAST doesn't have a lot of like built-in things. It has Roscoe if you want the defaults. But it's really also have lots of interfaces for you to do what you want to do in control. So it's really lots of options for implementing your own ideas for control. The actual, of course, turbine configuration is key. So the geometry, masses, stiffnesses, as I mentioned, we'll talk about in more detail. We don't represent the tower, the blades as full three-dimensional, shells or solid elements. We're just saying they're beams. So we need what those beam properties are. Classic EI stiffness, mass per unit length. These are the kind of things that you need to give in the code. And also we'll talk about, at least if you turn on Elastodyne, you also need the mode shapes of the blades in the tower. And so these are kind of the core inputs of OpenFAST. So first of all, for the airfoil data, generally what you have, with an airfoil, you do some, X-foil or R-foil or some wind tunnel test to get like a 2D airfoil data set, right? I know lift and drag for some limited range of angle of attack, usually just fast stall or something. In order to generate the full data files needed for OpenFAST, generally there's a processing step you need to do to make that happen. So we take our 2D data, we apply things like, let's go, in the aeroelastic simulation, you may have angle of attack from any range of angle, not just the, 0 to 20 degrees. So we extrapolate that airfoil data out, usually using some sort of flat plate theory. There's also rotational effects, right? If I take my blade and I spin it in an operating environment, you get what's called rotational augmentation. Usually stall gets delayed, and so your 2D data doesn't naturally apply. And so this airfoil prep tool is really what's doing that sort of data manipulation to take your 2D data and apply it in the three-dimensional environment. Also, the MON model you can use from DTU generate data, but generally the inputs to that are things like wind spectrum or coherence, obviously the profile of shear and veer and so on. That's what's feeding that solve. But usually you run things like TurbSim or the MON model ahead of time, and you feed those wind data into OpenFAST. Again, I mentioned for the controller, Roscoe is the tool Enel provides to give you a nice baseline controller. I would say relative to an industry controller, Roscoe gets you probably 90% of the way there. I think there's always like bells and whistles that the industry controllers really have that do a bit better. But Roscoe gets you a nice baseline controller. Of course, if you have your industry, you have your own access to your controller, you can obviously do better than that. Beam properties, again, usually, if you're talking about like a blade, you have some composite layup of some complicated structure. In the end, you need a beam property. So we have tools like On-Before or NUMAD, which is tied to ANSYS, to give you those beam properties from much more sophisticated layups. So you get another pre-processing step you do. And for mode shapes, again, only Elastodyne needs mode shapes. It needs tower and blade mode shapes. We have tools like V-modes or Frame3DD that can generate those mode shapes based on the beam properties themselves. So this is like the pre-processing steps. For post-processing, so once you sort of run OpenFAST simulations, there's lots of different kinds of output. The natural one, from nonlinear time domain simulation is time domain output. There's different post-processors. I think PI.View has become our popular one. I have at the bottom just because I added it at the last, but it's probably our most popular tool, and it's something Manuel wrote. Does all sorts of things, plot time series, it can compute PSD, statistics, all that sort of stuff you would do with simulations. Some of the older tools like mCrunch, mXtremes, mLife can do some things. PeakCrunch, I think, is taking over. That's our Python version of all those post-processors. So those are kind of, if you're generating linearized models, the other big part of OpenFAST, I think the typical post-processing we're doing is some sort of MVC transform, because OpenFAST will generate periodic linearized models. We'll talk a bit about that. So you usually post-process that with some sort of MVC. And then the other thing that we do in terms of output is visualization. So OpenFAST can output basically VTK files that you can open up in ParaView and actually visualize what's going on in the simulation. And then finally, in terms of the process, again, I would say You never run an OpenFAST once. You really run lots of load cases, and NREL has been putting in all our effort. I think a lot of users have wrote their own scripts to do these sort of things. So I think we're trying to put all our effort in making WISE more user friendly to enable that process with community. So WISE is where you say, I don't run, IC load cases 1.1, 1.2, blah, 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 blah. You specify that in WISE, and it would do all the work for you to basically run through that process. But that's at a high level is what you're going to be doing with the tool. And then finally, just mentioned verification validation is key. Again, at the end, I have what we've recently been doing in this space, but I would say, the model is only because it's not resolving all physics, the model is only as good as the inputs you have. So garbage in, garbage. Formalize a region of confidence, where we trust the models, you apply it in this space, but if you're doing something way outside where we've ever validated, recommend you doing some homework there. But I would say that's really key. It's getting a combination of high fidelity and real world data that's leading to that validation exercise. We have lots of papers on that topic. Anyways, that's a high level. Again, now we'll start diving in, but any questions before we dive into details? So they're only needed if you're running Elastodyne for the blades or the tower. And I think we'll clarify that once we get to the Elastodyne section, why it actually needs that. Because you see, Elastodyne also needs the beam properties. So why does it need the mode shape? I'll actually explain that once we get to that point. So save that question. But if I don't answer it, please ask it again. Yeah. Not like a fully automated, like here's a bladed file, here's an open. Talk about some of that, I'm not sure.
Those have some people, they have had a chance to
Yes, the Hawk 2 is definitely a little more closer. And it's also like a little dangerous. We try to be like, we have some government funds, obviously, to push a lot of this. We're not trying to compete with industry, but we are trying to push and make things better. So having a direct converter may be a little, but yeah, I mean, we definitely have some tools to aid in the process, but not something fully automated. Okay, so this next section, what we're really going to do, and I spend a lot of time in this section just because I think it's like fundamental to understand OpenFAST, is the framework itself. So I won't be talking about any specific module like arrow or structure here. It's really about how does this thing work together, because that's key to understanding this both the code base as well as how the models, as you see it in the input files, everything is sort of tied around this framework. So I'll spend a bit of time on here before we start jumping into each module. So yeah, overall, what the framework is a way to basically take components of the system and couple them together. One of the unique things I would say about OpenFAST is, we have these 20 modules and you can run them all sort of coupled together, but you can also pick any independent one and run that isolation. So I can say, if I just want to look at arrow, I don't want to worry about aeroelastic coupling or control. I just want to say, what is the aerodynamics going to do if I independent of everything else? You can actually take Aerodyne and run it as a standalone solver. Likewise, within any other modules, we have basically drivers for every individual thing. So if you want to focus on something, often that's used for like either prelim design, or if you're trying to figure out what's wrong, it really helps to just focus on that thing. So that's a key part of our program. So we call basically the together, and we call that the glue code for OpenFAST. Physics systems, there's like a monolithic solve, meaning you kind of write every equation together into one big thing and you solve it as one thing. That's really actually done in a big multi-physics system because it's usually quite hard to do. Generally, what we have is a partition model, where we have an aerodynamics thing here, we have a structural thing there, we try to make it coupled. In that partition model, we distinguish between what we call loose coupling and tight coupling. And so by loose, I mean that module has its own solver that's solving its equations. So, you know, if it's an ordinary differential equation, it's solving that differential equation in time and time advancing. If it's an algebraic thing, it's doing that. But it really is we've actually introduced now tight coupling into OpenFAST, at least for some of the modules. That's where we basically take one solver and you solve. Historically, OpenFAST has been based on loose coupling. And in that, there's also two more things. There's like implicit and there's explicit. I also talked about that on Tuesday. By explicit means that basically I can sequence these modules in a certain way. You know, say structural first, calling, you know, my structure is doing this. I pass that to the aerodynamics model, and that aerodynamics model gives me a force back, and I can kind of sequence them in some way. That works great for things that don't have what's called load acceleration feedback. And hydrodynamics is a great example with a load acceleration feedback where, you know, the hydrodynamic force mass effect where, you know, that force depends on the acceleration of the body. And so I can't calculate the hydrodynamic force until I know the acceleration. And so you're kind of stuck. And so we solve that implicit problem directly in OpenFAST. And we'll talk a little bit about how we do that. But again, I think you have to understand some modules are implicit, some are explicit in the solve. So a little bit about the framework itself. These are sort of what we thought of when we came up with the framework. It makes sense for its module, so it has to have, you know, independent inputs. So I kind of draw on the left. The inputs are what sort of, you know, what this module is receiving from something else. It's not like I try to distinguish that from like the input file where you're just defining like constants of the model. This is more like, what does that model need to do its solve? Because it's probably not independent. It needs, so again, aerodynamics, you know, it needs to know that there's the structure there and the structure is moving in some way. So that's like an input to the aerodynamic solve. Vice versa, you know, the aerodynamics module is probably producing some force that gets applied to the structure solve. So you can kind of see what's going to happen there. So, you know, if that was the aerodynamics module, the inputs are structural motions, the outputs are forces, and inside it's whatever, you know, it needs to calculate that force. So it has states, it has, you know, some fundamental parameters like the airflow polars or something. That's how we frame that. And so we wanted the modules to basically have their own, whatever makes sense for that module. That's how we define that. So the states of the module can be basically in four types of forms. Continuous time, that's like if you have an ordinary differential equation that defines it. So, you know, if you have x, there's an x dot, and there's some derivative there. There's also a discrete time state where maybe you've taken that continuous equation, you've discretized it in some ways. It's often used in control systems where, you know, if I know my n, I can calculate my n+1, but there's really nothing in between. It's only a discrete thing. So that's what a discrete time state is. We support that. We support constraint type states, what we call Z here. Those are like algebraic equations. You kind of see it there in the equations. So Z says, you know, I have something that's tying something else together, and there's some algebraic equation that I need to solve to make that happen. And then I don't have an equation for it, but we call other states. You can imagine another thing like a binary state. You know, is it true or is it false? We support states like that as well, or things that are not in the typical form. The reason I sort of specify a continuous discrete constraint is because that affects linearization a lot. And so when we, in the framework very much, you'll see it. You know, we have to explicitly say, is this a continuous state? Is it a discrete state? Is it a constraint? Is it something else? And linearization only supports the first three. It doesn't support binary states, for example. Loose and tight coupling we mentioned, and right now everything, you know, the version you have on your computers, it probably likely has loose. Maybe Derek has tight, but probably no one else does yet. But tight is coming soon, so that we're calling it 5.0. We'll have tight. Another key thing, and we'll talk a little bit more about that, is independent discretization. So a module doesn't have to have the same time step as another module. It also doesn't have to have the same spatial connection. Like if you're doing structure and fluid together, you know, structure and aerodynamics, say, the structural discretization does not have to be the same discretization that you're using for aero. They can be different. And we support the mapping between those structures in our coupling. Talk talked about this. So again, time domain simulation is important. Linearization is a key, and usually linearization is best about some converged operating points. So that's another part of the solve you'll see in there is how did we compute operating points for linearization. A couple more features of the framework we had is we want things, what we call data encapsulation. So we don't want global data to exist in the solve because that really makes code very messy. So there is no global data in OpenFAST. It's all like data is defined, but it's also defined in a way so data is encapsulated, but we can also dynamically allocate it. And we use this, for example, in Beamdyne. Beamdyne, for those of you who know, is actually a beam model, just a single beam. But of course, usually a blade has 3 of those beams, and one for each blade. And so what we've made it allowed is like with one Beamdyne model, we basically have, if you're running a 3-bladed turbine, 3 instances of Beamdyne running at the same time. And so even though it's one module, we can basically dynamically say there's more than one of those things and couple them together. So that's another key feature of the framework. So all modules can be dynamically allocated in that sense. The other thing that we wanted in the framework was checkpoint restart. Just means like we can pause the simulation and dump all the data and then restart at that point at some future time. So I think the equations, hopefully those make sense there. You also see where the variables fit. The states are basically within the module, parameters are within a module where they're getting inputs and they're computing outputs. And then the glue code is really coupling things together. Obviously, the glue code doesn't know anything about states. It doesn't see them. It only sees inputs and outputs. And so, if you want the glue code to touch a state, the state basically has to be sent as an output, as a copy. What the glue code is doing is saying, I have all these outputs from all these modules, and I know I have to calculate inputs. And the glue code basically says there's a big algebraic system I need to solve to make that happen. This output gets mapped to that input. So it's solving that U equation directly. Again, either explicitly or implicitly. Here are some examples of what those look like. As we talk through each module, we'll probably go into these more. But so what are some examples of inputs? I mentioned that. So the aerodynamics model, it's usually structural motion is an input. Likewise, the aerodynamic load is the output. For the structure, it's like the reverse of that. So it's like it's receiving loads as input and it's calculated motions as output. States. States for a structural model will be displacement, velocity. Say at the structure, there's states. For generalized dynamic wake has some continuous states. Hydrodynamics, has states and so on. Controls, you can kind of see generally. Again, we'll talk through these, but hopefully that gives you a sense of what these things look like in the framework. So how to solve? We had this. We thought through this like, well, there's all these interconnections between these modules, and that's be quite a spider web of nasty connections. And say, I don't want to solve it like that. What I really want to solve is just, let's have one common connection point. And let's solve a big algebraic system to make that happen. So that's how we've structured OpenFAST. And so this is how it works. And again, I talked about it on Tuesday. If you saw that presentation, I think I've already sort of defined what loose and implicit, explicit and implicit means. So here's what the algorithm looks like. Basically, it says, say I'm at time step n. So I know everything up to this point, and my goal is to get to the next step. So what it does is it says, okay, if I'm at n, some of those solvers, some of the modules may need some information at n+1 to solve. Simplest examples like backward Euler, familiar with that solver, like it needs to know n+1 data to get to n+1. So it needs to know something. So to make that happen, we first simply do an extrapolation of past inputs. We say, okay, we're at n, I'll look at n-1, that'd be a linear extrapolation. If I look at n-1 and n-2, that'd be a quadratic extrapolation. So you can do either. It just takes that past information and just guesses where it's going to be. With the guess, it's not correct, but that's the first step. The second step is, again, some modules are very explicit in nature, meaning you can sequence them in some way, and so we simply do that for everything that is explicit. So we have some information at n+1. We say, okay, I'll take advance this module, then I'll advance that module, and as I'm going through, some of those outputs are then feeding in and updating the inputs, so they're kind of overriding the extrapolation. But that's what happens in step 2. Step 3 is where we do all the implicit solves. So things like hydrodynamics, structure coupling have an implicit solve. So we basically do that solves together in a big Newton scheme. That's just taking that U constraint and basically solving it directly. So there's a big Jacobian that gets solved there. Step 4 is like step 2. Is some things depend on the implicit module, so they happen afterwards. And so then now basically everything's advanced over, but we know that some of those modules were not fully advanced properly because they were based on some extrapolated input. So that's where we have basically a correction step that happens. Like, okay, well, I can try it again and just go back. So I basically throw away the extrapolation. Now everything's already advanced, so I don't need to extrapolate again, and I just try again. Generally, there's a balance. You know, if you take a really big time step, you may need lots of corrections to make that work. Otherwise, you can also just drop the time step way down, and then the extrapolation is not doing much, and you don't need any corrections. So usually most of the models, if you find them in the examples, actually have 0 correction steps. But some of the modules, may require 1 based on the time step chosen. Anyways, that's how the algorithm works, at least loose coupling algorithm. Again, I would say this is great. It works well. It's numerically converged, it's stable, but some models require very small time steps, which is unfortunate, and that's what the new tight coupling will solve that I showed on Tuesday. A little bit about mesh mapping. Again, our arrow and our structure, or a hydro on a structure, there's some volume there. There's some spatial boundary where they connect. And when you look at OpenFAST, you'll notice actually I'd have to discretize it twice, like once for the structure and once for the arrow, or once for the hydro. You may be like, why do I need to do that? And it's really about trying to, make that the module we want, to make the module make sense for that module. So for like a structural model, if you look like stiffness along the blade, like it's really high stiffness at the root, and it quickly tapers down as you go along. So generally for like a structural model, you probably want a pretty fine discretization near the root where that stiffness is varying greatly. Aerodynamically, it's almost the opposite. Like usually that tip effect, tip loss is quite important. So you may want to heavily discretize the tip. And so you can kind of see like structure and arrow are not really great matching. So what we allow here in OpenFAST is that each module can be discretized however you think is best for that module. Right now we support 2 kinds of meshes in OpenFAST, just point meshes and line meshes. So points are just like a point cloud. So basically it's like a series of points in space, but there's no connectivity between them. So you can imagine these are like rigid bodies or concentrated loads or something. Lines are like, a beam, which is generally a line element. So it has some like this node and that node are connected by something. And our mesh mapping uses the nature of the mesh and the mapping. I'll go through an example of what that looks like. So at each node of this mesh, there's first of all a reference, like a reference configuration, like that mesh naturally wants to be in this position with some orientation to it. So it's like a reference location for that mesh. And then, so that's like kind of considered that like a parameter of the mesh. Whereas each node also has either like an input or output associated, that what we call the fields of the mesh. And these can be things like the motion or loads. So maybe it's scalar quantities like color or something if you want to track that. But that's sort of like the inputs and outputs that get stored in the mesh are what we call fields. And I won't go through all the details of the mesh mapping, all the math there. You can see there's a nice paper on that. But so some of the main highlights, first of all, they support extremely disparate meshes. So this is showing an example of like a jacket structure where really hydrodynamically I made it like a full jacket structure. But for structurally, say I don't really care about all the individual loads and the members. I could do that, but for now I just want to say it's one beam. That's my jacket. I just want to know globally what it's going to do. And actually the mesh mapping allows those things to get mapped together. Right now we support all the coupling. So if one module has point, you can couple that to a point. You can also couple it to a line and vice versa. Let's see, it supports large motion. So these mesh mappings have no limitations. So if you bend like a blade in a circle, like the mesh mapping is still valid. And it's, relative follower, we won't talk about that. Let's see. Guiding principles of the mesh. First of all, if the meshes are like completely one-to-one, so I do have arrow and structure on the same mesh, the data will transfer completely directly. Like there's no information change there. But if they're not, then the data gets, like if it's a line mesh, effectively, if the lines aren't fully lined up, the data gets like interpolated, if that makes sense. Next sort of theme is that the rigid body motion is maintained. So if there's an offset, if I have a point element here that I connect to this one rotates, the other one's got to move with it, like as a rigid body. If there's an offset, it's like connected rigidly. They're also conjugates, so loads and motions are basically happening in conjugate pairs. I mentioned that one. The first one, I guess, was on if you're transferring load from one mesh to another, the mesh mapping ensures that the overall force and moment are consistent. So it's like we're not losing information in the transfer. So here's an example of what that looks like. So I'm just going through two modules, and say the first one's like a structural model that's a very simple model. It's a single rigid body you can represent as 1 point. So like a rigid rotor, say that there it is, 1 point. Its input is load. I want to know how that body's going to move, and I want to output its motion. And I'm connecting that to module 2, which say is an aerodynamic model that I've actually discretized the blade. So I have a bunch of nodes along the blade where I'm computing forces. And of course, to compute those forces, I need to know what the motion of that structure is. So that's what we want to map together. Again, they're not the same mesh. So obviously, they're very different meshes. So here's an example of how that would work. So I take my single node from my structure, and I want to displace it 2 units in X and rotate it 20 degrees about X. What that's going to do to the other mesh is it's going to move it, and it's going to rotate it as rigid body, if that makes sense. So like that thing is going to rotate. And so it's not just, so the displacement is not just based on displacements, it's also based on rotations, so that rigid body coupling there. Likewise, I take that load and I say apply a nice uniform load on that blade. And now I want to map it back to the structure. And so I basically integrate that force and I apply the total force to my structure. And also that force, because some of those nodes were offset from my structural model, will also create a big moment arm, like shown there in red. So the forces create the torque. So again, the total force and the total moment are balanced in the mapping. So that just, again, all the math is in a nice paper if you want to see it, but that's how the mesh mapping works. And does that make sense? So hopefully what we're trying to do there. But that's anytime you have sort of independent discretizations that have offsets between them, this mapping will happen in the background. Okay, and next topic is on linearization. This one actually, I find linearization, it seems like linearization, that's easy. That's a linear model. I find most questions actually are more tied to linearization than they are for time domain simulation. I think it's because there's some fundamental thing of what is the linear model really giving you. So a little background on that. Already said linearization is about understanding, lots of things it can be used for. Actually, most functionality these days is linearizable. You can see the modules that we currently support. Where we don't linearize is things like other states, binary states, we can't linearize those. Right now, we also don't support discrete state linearization. So some things like the unsteady arrow models like Beddoes-Leishman are discrete state form. Right now, you can't linearize with those, but we have continuous state versions like the HGM model that you can linearize. And let's see. Key point always with linearization is that it really represents a perturbation. So the truth system, of course, is nonlinear. So linearization is always talking about a perturbation about some point. And so what that point is pretty core to understanding linearization. So this is showing an example where I have, say a module that has differential equations, it has some constraint, and it has an output function. And say I find an operating point, what I'm calling underscore op there. That applies, of course, to this input I'm showing, but also to the constraint and to the state. So I say, okay, I have some operating point now. And what I really do with linearization is I say, okay, some perturbation, delta U or delta X or delta Z about that operating point. So if you linearize that equation, you basically look at all the Jacobians of that, the Jacobian of the continuous state equation with respect to the state, with respect to the constraint, with respect to the input. There's lots of Jacobians that show up there. So for this system of 3 equations, there's actually 9 Jacobians for all the combinations there. The nice thing is once you linearize, the constraints are really easy to solve. Like if it's a linear constraint now, I can algebraically eliminate it. So that's what we do in the solve. So when you actually see the linearization, even though you may have lots of constraints, you don't see necessarily the constraint in the result because effectively we've eliminated it already. Once it's linear, it's really easy to do that. This is showing an example. So that A matrix for that simple system will not just be, partial X with respect to X, so that Jacobian also has the constraint effectively in there, enforced in the solve. So that's how we do that. And then if you look at it at this level, you see, imagine at the glue code in terms of time domains. The time domain is shown on the right, sorry, on the left, and linearization is shown on the right. So in the the time domain, each module has its continuous state function X, its constraint Z, its output function Y. Each module has its own thing, all coupled together through some U constraint. So that's what it looks like in the time domain. There's some funny math, there's cool math that says all those constraints and all those inputs effectively make one big constraint. That's what I show on the bottom there. So in the linear sense, what we do is we do something very similar now. So each X, Z and Y becomes some sort of state space value of A matrix, a B matrix, a C and a D matrix. The glue code is also linearized same way. So like you have the change of constraint with respect to the input, as well as the change of constraint with respect to the output. So those Jacobians are in there. And effectively, we condense everything down, eliminate all constraints. We have a final ABCD system. So that's what we do for linearization. So we basically linearize each individual one, and then couple them together by linearized constraint at the glue code level. You may wonder how we also handle perturbations of inputs in that process. So if I say, aerodyne is coupled to my structure, what happens if I perturb the aerodynamic force? You can actually see that in the model as well. So we basically add a perturbation in that process. You see it what we call the delta U plus. It's like a perturbation on top of what the algebraic constraints already enforce. So you really can see it. So any input in the model, you can basically think of as as in your input vector of your state space. But it doesn't have to just be a control input. It can also be aerodynamic force or a structural motion. As long as it's an input in the system, we can see its perturbation through the model. It's quite a useful feature in the end, I think. So this is showing an example where I have these modules here. Again, each one's been linearized. Glue code's been linearized. I combine them together, and you can see like there's the equation that we use to calculate the final A matrix. Effectively, again, we've eliminated all constraints, which means that the total A matrix doesn't depend on each individual A matrix. It also depends on, you can see it there. It also depends on the B matrix and the C matrix. And I don't explain what G is there, but it actually has all the D matrices in there, as well as the glue code stuff. So effectively, everything gets mapped together in the end. So while I can look at linearization of elastidine, say as an example, that has the mass, the stiffness, and the damping of the structural only. If you look at just its elastidine linearized system, but if I look at the full system linearization, that has the full air elastic effect. So it has, air elastic damping and air elastic stiffness and so on. So that's the key part of this linearization. Hopefully that generally gives an idea of how that works. Quick summary of some other features of OpenFAST. Where are we in time? Okay. Visualization capability. So again, OpenFAST doesn't directly, there's no GUI to OpenFAST. You don't directly see it when you're playing with the input files, but an output of OpenFAST can be VTK files. And then there's open source tools like ParaView. Other tools are available, but basically you can read those in and then see what that simulation is doing. You can do that for linearization. Sorry, like time domain simulation. So the time marching, you can run it through, actually visualize what happens. Visualization would be either like a surface geometry, like shown on the top, or you can just say I just wanted a stick figure representation. The surface just gives you some visual, press your boss or whatever with what it's doing. Yeah, also you can do for mode shape visualization, and I think Derek had a nice presentation on that on Monday. Yes, I think this is the last feature mentioned. Again, checkpoint restart. This is really about basically all the data as you're going through. You can pause the model and basically dictate a restart time period. This is mostly useful for long simulations, like if you're potentially going to lose power or your HPC, often goes down, which happens at NREL a lot. So either really long simulations or, OpenFAST coupled to some CFD solve. Like I don't want to, run for a week and then have a hiccup in my computer and then have to start it over. So you can basically define checkpoint files as you go along. And then if something does happen, you can basically restart again at that checkpoint. So basically what that means is all the states and all the inputs Of course, all the parameters get dumped to a file, and we can start up at that point again and keep going. Finally, in this section, I think just to be clear, we do use an Apache license, so it's not a GPL license. If you know these licenses, Apache is really just a very flexible license that basically indemnifies NREL. So if you download OpenFAST and you're a turbine OEM and your turbine collapses, for some reason, this indemnifies NREL. You can't blame us for that. But it also doesn't restrict anything. Like if you want to download OpenFAST, use it in your own solver, change something, there's no requirement like GPL would be to push that back. So it's a very non-restrictive license. So it basically just protects us, is all. There's actually been a few companies that have, that they take pieces of OpenFAST, they plug it into their solvers. They're going to think of Simpac as an example. They want their structural model, but they use Aerodyne or Hydrodyne, and they can basically repackage that. Apache allows them to do that. GPL would not allow them to do that. So, anyways, that's that. Pause there again. Any questions on the overall framework? That's how we basically couple things together or run them independently. Yeah. Yeah, I think Emmanuel will get to it once you start looking through files. But basically, there's a section in the file. Time domain is always sort of natural. Like you say, how long you want to run it. There's also a linearization section that says, is this a time domain simulation that we're also going to be linearizing? If you turn that on, that first checks a few things. It says, okay, is this model actually linearizable? Again, does it have binary states in them? I can't linearize that. Sorry. Does it have discrete states? No, I can't do that either. But if it is really linearizable, then you define the linearization, and there's a few input options there, like like how to find the operating point. Like when should I linearize? Do I want to linearize just at given time steps? It can do that, or you say I don't want to linearize until I get to some steady state solution. Like I reach some equilibrium point. Now I want to linearize, and you can define what those things are in the file. So I think Emmanuel will talk through that a bit. Does that make sense? Like it's up to the user how to do linearization. But almost any simulation can be linearized. Right. That's a great point. So yeah, so fast is always nonlinear, but it can export the linear equivalent. What you do with that is up to you. So you can, compute an eigen solution of it. You can take the linear system and time march it yourself. You can do lots of things linearly. Anything else in the framework? Okay. Great. The next section is really just kind of stepping through some of the core modules of OpenFAST. So we'll talk about some key modules. Won't go into great detail on any of them because that would take too long. Hopefully paint the picture of what these things are so that you know how to use them. First of all, the sort of central structural module of OpenFAST is called Elastodyne. If you're familiar with, say, Flex code that's used in industry and originally from DTU, it's very similar to Flex in the sense, it's a fixed configuration, so it's not completely arbitrary. So right now we have, it's only horizontal axis, can't do a vertical axis here. It's 2 or 3 blades. Actually, I think you add an option now. You can add more blades if you want, or 0 blades. But you can choose how many, but you can't, it's a hot in the end. You can have the rotor be upwind or downwind. The hub can be rigid or teetering. Let's see, we have tail rotors with tails. But this basically what the most fundamentally it looks like this, other than the tail. There's blades, there's a tower, there's a shaft, there's a nacelle, and then now that sits on basically a 6 degree of freedom rigid body motion. That's what's in Elastodyne. It's limited degrees of freedom, so at the most it has is 24 degrees of freedom. And some of those are, I use the term modal carefully. I think I explain it better on the next slide. It's more like a Rayleigh-Ritz method, if you're familiar with that, and I'll explain that next slide. So, but the blades in the tower follow this modal or Rayleigh-Ritz method, and the rest of the degrees of freedom are more like a multi-body type model where they're, either translation or rotation about some joint. So you can see it in terms of the modular framework there. Again, the states of this model are displacements and velocities. Parameters are things, all the constants of the model, the geometry, the mass, stiffness, structural damping coefficients, gravity is a parameter. Again, the inputs would be the aero, the hydro loads, whatever the controller wants to do goes in. As you'll see, the elastine can be coupled to subdyne for the support structure. And so there's also reaction force that comes up through the support structure. If you have subdyne on, that can send reaction loads up. So that's basically at the platform base. We have 6 degrees of freedom that connect to. So if you want that to go to like a jacket with lots of degrees of freedom, that happens through this coupling at the tower base. And the outputs of the module that get used by other modules, so, displacements, velocities, accelerations, and reaction loads in the system. So again, more about degrees of freedom here. First of all, about the degrees of freedom are generally flexible. There's a couple specific constraints. For the rotation of the platform, right now we require there's some small angle assumptions that go into that. So you can't pitch or roll or yaw more than about 15 to 20 degrees. About 20 is about as far as you can take it. Otherwise, there's some small angle assumptions that go in there that can result in inaccuracies. Often you say small angle is maybe 5 degrees, but we actually do this, what we call correction for orthogonality shown there. So that's the linearized, Euler matrix. If you take, like an Euler sequence, you write that all out, you linearize it, you get that matrix with ones along the diagonal and the theta's on the sides. We don't actually have that implemented in the code. We have the one on the bottom, which has a bunch of square roots and nonlinear terms in it. So that allows us to go from 5 degrees to, again, about 15 for these angles, but not really beyond that. And so we use that, again, on the platform rotations. We also use it for the blade and the tower deflections. So if your slope is more than 15 degrees, it starts losing a lot of accuracy. The rest of the degrees of freedom, like generated rotation, obviously it can be large rotation, it could spin forever. Yaw, everything else is basically large. All displacements are large. Again, it's nonlinear. So we have things like the Coriolis forces, the gyroscopic forces are in there. In terms of the beam model, so again, the user has to specify the stiffness and the mass distribution. But we also force the user to give it the mode shape of that, and that's really because of the boundary conditions that get applied. So what the mode shapes you're providing as input really are basically the shape functions that this finite element model uses. So again, it's like a Rayleigh-Ritz approach where you say, here's my shape functions, solve it with that. I was going to say that generally, because we only have a few shape functions available, a few degrees of freedom, you want to choose shape functions that represent the real modes, or it's not really a good basis. So generally recommend you use actual mode shapes as basis functions, but you can choose other things if that makes sense for your problem. And let's see, some of the limitations of the beam model is, first of all, it's Euler-Bernoulli beam, so there's no shear terms or torsion. Well, yeah, I guess there's no torsion or shear in there, so it's really bending only. The beams are straight and isotropic. That's quite, maybe that's fine for a model tower, but for a blade, that's, fairly limited these days, I would say. Bending only assumed mode method, that's a Rayleigh-Ritz approach. And then I hate to use the term modal because it's not. There's actually quite a few nonlinear terms in the solution. Again, there's gyroscopic terms, there's Coriolis terms, there's what we call the radial shortening effect. So as the blade deflects, the root's getting closer to the tip. So these geometric nonlinears are in the model, all based on this shape function code. So yeah, often people say, well, it's using mode shapes, it's linear. It's actually not linear, if that makes sense. There's quite a few nonlinearities in there, but the mode shapes are used as shape functions themselves. Anyways, that's all I have on elastine. Hopefully that makes sense, but happy to take any questions on that. Please. Great point. Thanks for clarifying that. So with blade, usually you can say it's just take the blade clamped, and that's the mode shape that generally works. But for the tower, what you said is really important. So for the tower, we generally say, to get the tower mode shape right, you need to know the top boundary condition. Of course, that's free, but there's a big mass and inertia that shows up there. And then if it's not a land-based system that's just clamped at the bottom, if it's like on a floating platform or a jacket, like whatever that stiffness or mass of the floater or the platform it's on, that boundary has an effect on the mode shape, of course, of the tower, and that's the mode shape we really want to give here. And thanks for mentioning that. Sounds complicated, but there's tools that enable that calculation, like the beam modes of the frame 3D that I mentioned. Okay, next one module I'll mention just one slide on this one, Beamdyne. So as I mentioned, and I love this picture from Kenneth Thompson, who was at Siemens. I don't know where he is these days, maybe at DTU again, but showed the blade design, from what it was in the 90s, I think when the last time it was only first made, Flex as well, to what blades look like now. Obviously the real blade now is much bigger, but if you scale it the same length, that's what it looks like. It's like the blade is like, before I could say, oh, it was, straight beam, yeah, probably. Now it's definitely not a straight beam anymore, and there's composites in there, it's composite coupling. So this is, Elastomine was great, I would say, for older blades. For nowadays, Beamdyne generally makes more sense. So we're really trying to solve that more advanced blade. First of all, Beamdyne is based on geometrically exact beam theory. So it's different than like the Hawk 2 approach or the bladed approach, where it's like a series of linear fine elements in some co-rotational formulation. We don't use that here. We actually use a geometrically exact beam. So you take the, so every cross section can have a full 6x6. So you have bending, can have stretching. Those are usually coupled. Shear and torsion are in there, and you can have any coupling between bending and torsion as well. So it's a fully populated mass and stiffness matrix. Damping is fairly limited right now. We just have a stiffness proportional damping. We may change that in the future. Maybe Pietro commented earlier in this conference, like there's some limitations with stiffness proportional, but that's what it is now. Geometric exact beam theory it works for straight blades, but also works for curved blades. So if you have a blade like that that's naturally swept, you can build that curvature in the model, and there's terms that show up because of the curvature. And it's completely geometrically exact, it's linear elasticity, but it's geometrically exact. So that blade, again, you can bend it in a circle, and like the beam theory is still valid as long as linear elasticity at cross section still applies. So there's no limitation of geometry. So like last line is limited to 15 degrees. This thing can go 360 degrees. No problem there. We use a Legendre spectral fine element implementation instead of you can see it there, talk about structural analysis. There's what we call H refinement or P refinement. Where H refinement is you basically add lots of elements to add more fidelity. Here, we basically just increase the order of the element. So actually the Beamdyne is basically one element almost every time. You say, how many nodes do you want in that model? And that determines the order of the element used in the solve. So it's what we call P refinement. We chose that because it basically has this exponential convergence. So with fewer degrees of freedom, we can get the solution more accurately than if we had lots of elements. In terms of the integration of mass and stiffness, the model supports Gauss quadrature or trapezoidal rule, but we generally use trapezoidal rule. That tends to be the better option. And the model supports both time domain simulation and static solutions, although usually when we couple OpenFAST, we're only doing time domain part of that. That's all I have on Beamdyne. Again, you can see it like in the module form. Same thing, states are like displacements, velocities, parameters are obvious. Inputs very similar. Aerodynamic loads come in, motion comes out. What's maybe fairly unique here is that the coupling to the this actually gets coupled to Elastodyne. So if you say I want Beamdyne, basically the blades in Elastodyne go away. You have a hub in Elastodyne. Now I have a Beamdyne coming and connecting to it. And again, we basically have this implicit coupling where the motion of the root of the hub is going into Beamdyne. So here's the motion I want you to use. Give me the reaction load back so I can self-press the turbines. So you can see that there in the input and output scheme. And that's definitely an implicit coupling that we have to solve in the process. Aerodyne, get a high level on this one. Aerodyne really has two sort of wake models. One is a BEM-based approach, momentum-based approach. There's like a quasi-steady BEM. There's also a dynamic BEM, what we call deBEMT, which basically adds some delays in that BEM calculation. So there's BEM, momentum-based approaches. You also have higher fidelity model, which is this free vortex wake model called OLAF. So that's for the wake. You can choose either one, or all, I guess in any of those three, BEM, deBEMT, or OLAF. Most production runs, where I would say we use deBEMT, but if you're really trying to study things with large deflection or large skew or shear or something, OLAF is quite useful for that. Let's see, at the airfoil level, you can have quasi-steady. That just means that whatever the polar says, this angle of attack will lead to that coefficient directly. Yes, we have that. We also have lots of unsteady airfoil models where there's some hysteresis involved in the polar. So whatever transient of angle of attack or relative velocity comes in will dictate what the next coefficient will be. So there's obviously states that happen to make the hysteresis happen. Yeah, so you see it there, and maybe this is not fully up to date. Continuous states should really be the deBEMT, of course, has them, but there's also continuous time versions of unsteady aero. So I need to update that slide. Sorry about that. So yeah, continuous time, like HGM model, is a continuous time unsteady airfoil state. Discrete states in this model, like the dynamic stall model of Beddoes-Fleischmann, is written in discrete time forms. Can be quite accurate, but it can't be linearized, unfortunately, very easily. So there's where you see discrete time states. There's also constraint states in the solve. You can imagine the induction in BEM. It's a quasi-steady thing. So that effectively ends up as like a constraint state in our solve. Parameters, of course, geometry, airfoil data, and air density. Let's see. Don't really have anything here, but tower right now is quite simple. You can have a tower drag model. What are the aerodynamic loads on the tower? You can also have there's a few influence models. So there's an upwind bow wake. Sorry, I don't have any detail here, but what does the flow around the tower do to the aerodynamics of the rotor? We have a upwind wake model as well as a tower shadow model for that. Then OLAF is again a much more sophisticated version of the wake calculation. It's based on basically a hybrid lattice filament method where the near wake is this lattice formulation, and that all gets rolled up into filaments, root and tip for the far wake. And you can choose how much you want of each. Lots of Biot-Savart calculations, that relate each of those vortices to the induced velocity. And with all these free vortex wake methods, I think that always the issue is the singularities that happen at the core, and there's quite a few regularization options available in OLAF to handle that. And this one can be expensive, but there's an OpenMP parallelization option for that one to make that quite a bit faster than it would otherwise be. Again, it's high level. You can find a lot more detail on that if you want to use that module. Again, please ask questions if you have any, but move along. If not, inflow wind. This model is pretty simple. There's not really much in it. It's mostly a way of just passing whatever wind data you want to use into the solve. And so it actually has no states. So the inputs are like what's the motion of my structure, and the output is what's the wind going to be at those points. And the parameters are really whatever the undisturbed flow is that you're trying to push through, whether that's uniform flow, some time varying gust, like the IEC ECD event or something. Full field turbulence is typical input here, where you're either using TurpSim or MON to generate some full field turbulent flow. Also has user-defined options, but again, very simple model, basically just a way of getting the wind data into the solve. Servodyne, also mostly quite simple. As I mentioned, most controls tend to be, at least in industry, not available to the research community. So you have lots of options of how to kind of implement your own controllers into the solve. Let's see. What Servodyne does in general, it's doing basically all the control and electrical drive functions. So things like, pitch controller, the torque controller, the cell yaw controller, a brake. The generator, if you're modeling details of electrical drive, would be in here. There's a couple other control options that we have. There's you could have like cables in the model that you want to actively change the tension of. That happens in substructures. In some substructures, we have that capability. There's also some control options like passive tune mass dampers. If you want to place a TMD in the nacelle or the tower or a blade, there's an option in there. So there's a few states when you have those things. Another thing about Servodyne and the structural control models allows you to apply your own forces anywhere in the system you want. That's a pretty powerful feature. You can define as many structural controllers as you want, meaning basically points in the blade, the nacelle, the tower, the substructure. Say, I have points all over the place, and each one of these points you can either put a TMD, TOCD, or a point force that you define. So it's a pretty nice, flexible way of just adding forces or damping elements to the model. And then the implementation of active controls. There's a very few simple built-in ones. I think Roscoe is sort of our go-to controller. What really Roscoe is it generates a bladed style dynamic library that you can interface to OpenFAST. But it doesn't have to be Roscoe if you have a bladed model. I had a question about bladed earlier. So if you have a controller already written for bladed, you can interface that directly into OpenFAST. We also support things like a Simulink interface, where basically OpenFAST is a block in your Simulink model, and you can build all your control signals in that block. We had a LabVIEW interface that's still only available in FAST 7. We actually use that for like controls of our cart turbine at NREL for like hardware loop stuff, but we haven't really updated that recently. And yeah, for all these control options, you can also sort of override them. You know, say whatever my controller is doing, ignore that, do something else. You can override things in the input file. We often use that for all the fault cases. Like if my blade gets stuck, ignores what the controller is doing, or so on, you can build those into the input file. But anyways, pretty high level. Lots of options there for controls, but mostly interfaces to user-defined things. Cables and tendons, yeah. So this is mostly in, I think right now that only exists in if you have Subdyne on or Moordyne on. So those two modules, you can define elements of Subdyne or Moordyne as controllable elements. And then basically that we have a linkage between Servodyne and those modules to do some active control of that. So like if you have some actuator in your mooring system, you say, well, I want to, based on some tension in that line, stretch the line or shrink the line. That's the kind of controller we're talking about here. So really it's Subdyne and Moordyne support that interface to this controller. So that's mostly everything for land-based systems. Now we'll talk a bit about some of the offshore capability. What time we got? Okay, we get time to wrap this up. Good. So Hydrodyne. There's big changes here for those of you already familiar with Hydrodyne. In 4.0, we're actually taking Hydrodyne, we're splitting into two. One's called C-State, the others we're just naming Hydrodyne. But basically all this stuff here is about wave generation. And all this stuff will actually be moved into C-State. The next big release is coming. But right now it's built into Hydrodyne. So first of all, for waves, you can define irregular, stochastic waves similar to turbulence, or you can generate like a white noise. Maybe it's better to call it pink noise wave, where you have basically uniform energy over some frequency. For the irregular waves, the standard spectrums are in there. Pierce-Mauskowitz is the standard North Sea spectrum. John Swap is like the storm version of that. So you can choose, which spectrum you want. White noise is really like a uniform. It's really good. Maybe pink noise is better. It's a uniform over some frequency range. Really useful for generating things like REOs. You can also define your own spectrum if you have something in mind that you measured. You can feed that into the model. You can also, if you have your own wave data, like you know what wave data you want, either some time history of wave elevation or some full three-dimensional wave kinematics. If you know what you want, you can enter that directly. If it's a wave elevation, it will feed, it will calculate the kinematics from that. The wave doesn't have to be just one direction. You can spread the energy around. We basically use this linear splitting there. So we take that multi-directional spectrum. We say, well, it's really a frequency-dependent spectra multiplied by a directional spreading function. So we don't fully support a full, mega beta combination, but as long as it can be separated out into one times the other, we support that kind of spreading right now in the model. And that just allows you to take that wave, like the top shows a multi-directional C states. It's mostly in one direction, but some of the energy gets spread to other directions. The waves right now in Hydrodyne are supported as either first order, which we call airy waves, or second order. The plot in the middle kind of shows an example of what that looks like. The red curve is like the linear part of the wave, and then that carries 90% of the energy. So what color is that? Green. The green curve shows the second order components, which are either there's two things happening there. There's a high frequency effect that happens, and there's a low frequency effect that happens. And that's basically allows you to do if you're familiar with hydrodynamics, the free surface is where all the nonlinear areas are at. That's quite nonlinear, and we basically take a first and second order representation of that. So you can go up to second order accurate here. You can't go higher than that right now in hydrodynamics. But this, if first order theory captures 90% of the energy, second order captures 99%. So we ignore that 1% at the end, have higher nonlinear terms. Yeah, so where you use second order is where most of the wave energy is in that primary wave spectrum range, but the second order energy is either at low frequency or high frequency. That can excite resonant modes of your structure. So it's quite useful to have that feature in there. The kinematics are based on second order Sharma-Dean theory for finite depth in there. So it's not a deep water relationship. It has the finite depth. They're just vectorially added to the wave. So we're not really doing any proper phasing of that wave current interaction. And then on the hydrodynamics side, so we have the waves now, the wave kinematics, and how do we calculate loads? Again, there's two main options in Hydrodyne. There's the strip slender members in the structure. So if you take a semi-submersible, you imagine there's like big offset columns and they're connected by a bunch of small braces. So the small braces and pontoons would be strip theory. And the big bodies where you have large volumes, that would be like potential flow solution. So in the small volume bodies, what matters is things like added mass, viscous effects. I guess there's a fluid inertia effect I don't have listed there, and then buoyancy. So I should say it's not just more like if you're familiar with Morrison's equation, that's the added mass, that's the viscous, that's the fluid inertia, but it doesn't have buoyancy. So we actually have had added buoyancy in that strip theory option. So they also have buoyancy in calculation. And this is great. You can have as many members as you want in any direction, jacket structure, multi-members, lots of elements as you want in the structure. It's completely user defined what you want. And then potential flow. These are, again, the large volume bodies where radiation and diffraction really matter. So that big volume body, like strip theory is really like wave transparent, like it doesn't, wave just goes by and it computes a force. But the structure is not affecting the wave. Potential flow, like that body is from diffraction, and as the body's moving around, it's pushing waves out and generating its own waves. It's radiating waves as well. So this potential flow solution is really based on the post-processing of a frequency domain solve, getting up to second order accurate. So it's not just the linear part, it's the second order part of that we have in there. Generally you use WAMET's the most popular code in that space to do frequency domain, but you can also use HAMS or what are the ones? Capitan is another popular one, and so on. So there's free versions of WAMET out there. But WAMET probably does the second order problem the best. So again, what you're basically taking from WAMET or low-like is like the REOs you feed them in, and you use that, or you take the 4 second order QTF and you feed that in there. Hydrodyne supports multiple bodies, so if you want you can have as many potential flow bodies as you want. You don't just have to have one. And those bodies can be computed independently, or they can have interaction between them. Imagine, for example, they could take an added mass matrix. For a single body would be a 6x6 matrix. You have two bodies, that would be a 12x12. And so by independent, I mean, it's basically a 6x6 and a 6x6, and there's no coupling between them. They're just solved as two separate things. But we also support the full coupling, so that 12x12 is really like a fully populated thing. So if you want that, those cross coupling terms, like what does one body do to the other, you can include that as well. In most models, I would say historically floaters were quite big. As we've gone forward over time, they've gotten thinner and thinner and thinner, like the Steesdale tetraspar or something. And so lots of models these days can be done street theory only, but certainly if there's a large volume in your potential flow, and so we support that as well. Again, you can kind of see how hydrodyne is split out with states. It has continuous states if you represent that potential flow solution in a state space form. We have that option. You can also represent it more typical. We do it basically with a convolution approach, which is a discrete time form. So the nice thing about state space form is you can linearize it. Again, if you want the potential flow solution in your linear model, you have to use the state space option. Otherwise, hopefully the rest of that's fairly clear. You get motions in, you compute loads as the output. Subdyne, that's our model for our substructure. And this one is based on a linear frame finite element model. And so this is showing an example, say, of that tripod structure there. So you take all those points are like nodes of your beam finite element model, each connected by some beam element. In reality, the model supports not just beam connections, it also has rigid link connections. We usually pair those with potential flow bodies. So if you have a big volume in your structure, like its flexibility is probably not important. And so we basically represent a big potential flow body as a rigid link equivalent in Subdyne. But you can also split up potential flow body in a bunch of sections and then represent it as a beam element. That's another option you could do. It's kind of up to you how you want to discretize your model. There's a nice question about cable elements. Subdyne also has, you connect two nodes by cables, which are really soon to be tensions. They're not like catenaries, they're like taut lines, mostly just like a linear spring, effectively. So those elements exist. And then the connections between elements, most connections are cantilevered. So there's one beam universal joint or ball joint. I think the key limitation with Subdyne is you can't introduce a joint that creates a rigid body mode. That's not allowed in Subdyne as long as the overall structure is like you can't have just like a beam with a pin connected to another beam that would flop around because the rigid body mode would not be solved properly by Subdyne. Subdyne solves this problem instead of just solving it as a bunch of beam, like this model here probably has 600 degrees of freedom in it because of all those beams. That would be expensive to do, but because Subdyne is inherently linear, it's meant for substructures that have small deflection. We take that in what's called the Craig-Bamford reduction. So we keep the lowest fundamental modes as dynamic modes, so they have a mass and a stiffness. Less than, say, 10 or 5 hertz. We want waves, but I still modes for to compute reaction forces and so on. And so we basically statically solve everything else. So we take all the modes, we say some of our dynamic modes, those can get excited by the structure, the rest are simply quasi-static modes. That's what we call the static improvement method. So Subdyne allows you to partition the model that way. You basically choose how many modes you want as dynamic modes. This is showing a tripod. You can also attach Subdyne to a floating platform. So like a semi-submersible there, you can have a bunch of beam elements to represent that. And while the deflection of the individual members is small, it also moves, as a 6-stop rigid body relative to everything else. So we do support the large motion of Subdyne when it's attached to Elastodyne, but the elasticity is still soon to be small, if that makes sense. Displacements, velocities are at states. Parameters, geometry, mass, inertia, force stiffness, structural damping. Those are all fairly obvious, I think. The inputs to Subdyne are the hydrodynamic loads that get applied, and then this connection back to Elastodyne again. So we have what we call the inner to Elastodyne above it. And so again, it's really the 6-stop motion, displacement, velocity, acceleration going in, and the reaction load at that point going back up to Elastodyne. The final module I'll mention is Mooredyne. So again, this is for the floating people, but say very similar to Orcaflex. It's this lumped mass formulation where it's not a continuous model. You basically discretize your line as a bunch of lumped masses with springs, and full nonlinearity of those springs is possible. So you get large displacements, geometric nonlinearities, but they're basically springs connected in rigid bodies together. You can do catenaries or you can do taut lines, no problem. Let's see, the stretching, in most cases, you can choose just a linear, EA type stretching of the line. Recently, there's been support for physical elastic elements in the model, where, your dynamic stiffness may be different than your low frequency static stiffness. And so these are also features that are now possible in Mooredyne. Bending's also been added, so we do have a bending stiffness term in there that's usually most important for the dynamic power cable. That's usually fairly stiff and bending. So you can turn bending stiffness on if you want as well. We also have a few specific elements, like if you have some nonlinear spring curve, you can build that into the model at discrete points. Let's see. Right now, most models with Mooredyne have what we call still water effect, meaning that you can have drag and add a mass and buoyancy, but there's no wave excitation in the line. But there isn't actually an option that's a little hard to use right now, I would say. But as long as you can put wave kinematics into Mooredyne, you can compute the wave excitation line. So that is possible, but it's a bit, I would say, user unfriendly right now. In the future, we do plan to add the direct C-state coupling so that data just gets transferred directly. Right now, it's as long as you provide your wave kinematics to Mooredyne, it can include that. Let's see, of course, the parent wave, the buoyancy line, that's all there. And there's also some seabed friction in that model. Just want to mention one thing about when you're doing offshore simulations is that there is a kind of a core limitation that we do have. Low case simulation where you're sampling the wind speed and the associated wave conditions. So you take it, say, from some C-state database like that, for this wind speed corresponds with that wave height. Generally, we do that when you run simulations, but that's really the only coupling we have between the wind and the wave. Like the wind input and the wave input are basically independent stochastic processes. There's no air-sea interaction solved in the solve. So each one can be powerful. First, the structure is feeling both, and it will respond to both. So wave will push the structure, and that may affect the air. So that coupling's there, but there's no direct air-water connection solve. If that makes sense. So keep that in mind. I think there's some great work at NREL on high-fidelity simulations of air-sea interaction. I'm curious what that's going to bring, and if that becomes important, we'll have to figure out what to do here. But that is a core limitation of this model. I'll pause there. Again, any questions on any specific module? Yeah.
then how OpenFAST is working. But for example, if I have no turbulence in my inflow, will there anything be exciting my natural frequencies as a base for flat side in the edgewise, for example?
If you have no turbulence, you're saying?
Yeah.
Well, there's still maybe rotation, so you can still get like gravitational excitation, you know, of the structure. But generally, you know, I would say the natural frequencies are getting excited by wind and waves. That's the main thing. The rotation can do it, but the wind and the waves are really. What's that? That will do it as well. So if it's a uniform flow, if you've turned on that what we call tower influence model for upwind, that means that the flow will like distort around the tower. So there's like a correction for the tower. And as the blade passes through it, you know, it'll kick it. So even for uniform inflow, you can get that effect. Yeah, so we're taking, I call it the lines of rotation. Maybe it's gravity or the tower influence, but that's still like a rotational effect. But yeah, it's in general though, it's the turbulent loading. So it's stochastic loading that's really the broadband excitation that's going to excite all your frequencies. Yes, that is in there, correct. As long as you turn on that influence model in aerodynamics. Okay. Yep.
I have two questions. The first one, for modern blades, is there any advantage of using Astrodyne over beamline?
Only that it's faster and easier to set up right now. So the last line is simple. Here's the EI stiffness, flap and edge. You can define a structural twist. So there's like a twisted function in there in the mass. That's it. And of course, mode shape. But if your blade's more complicated than that, you know, my blade is curved and every cross section has a, you know, bending, torsion, coupling term in it. That has to go to be done. So if you want curvature, if you want coupling, if you want shear, if you want torsion, you have to go to beam down for that.
For offshore substructure or for onshore substructure formation is handled by beam line?
A great question. So as I hopefully made clear, like Elastodyne and Subdyne are connected at one point. Typical approach is to place that point at the bottom of the tower. But there's actually no reason it actually is more flexible than that. You actually define where the point is in the model. And some of the models, like we have, imagine a lattice structure of a tower. You know, there's a bunch of beam elements there. You can actually do that in OpenFAST as well. You basically take that connection point and move it to the top of the tower. Effectively, you're basically telling the last line that the tower is a short little dummy, nothing, you know, you said length is epsilon. It goes away. So you basically move that point to the top of the tower. And then, then you could use Subdyne for basically the tower or lattice. Definitely needed if you have a multi-member tower. Like Elastodyne is only a mono, you know, tower, single beam. There's, you know, some disadvantages and advantages of doing that. So the advantages are like Subdyne has, of course, all the members. If you didn't want that, even if it's a mono tower, like Subdyne has torsion, has shear. Elastodyne doesn't have that. So if you want that, you could switch to Subdyne. Those are the advantages. The disadvantages are that it's linear. So like Elastodyne has some geometric nonlinearities to it. So as the tower deflects, then the cell is going to fall down a bit because of like the nonlinearity, geometric nonlinearity. That's in Elastodyne, but it's not in Subdyne because it's linear. So you have to kind of weigh the pro and con. For the tower, that's usually not a big effect. You know, may affect the natural frequency of the tower by 1% or something. The geometric nonlinear part, but yeah, you have to just accept that.
When you say Elastodyne, beam line as well.
A beam dyne is really for the blade. So for the tower, right now we don't have an option to do beam dyne for the. We could add that in the future, I think, but right now, yeah, the beam dyne is really for the blade. And the tower is either, you know, Elastodyne or Subdyne. Yeah, great question. Anyone else? Yeah.
I have questions as well. I've seen the past ticket solvers. So I'm not aware of any use of OpenFAST with structural solver, like more like a shell or solid basis elements. kind of limit properties. Is it possible? Has it been done?
Not by NREL directly, like in the fluid structure solve, we don't have any options in our code suite even to do, solids or shells connected to a fluid. Nothing in the NREL portfolio has that. Normally, what we do is we say in the time domain, neuroelastic fluid structure interaction solve, we say that structure is a beam, and then if we want to get to the detailed stress and strain of my three-dimensional cross section, we'll do that as a post-process structural analysis. So I'll take my shear forces and my bending moments at my cross section, and I'll pump that back into, say, new MAD ANSYS, and that will return me the stress strain in the actual structure. So it's that, like, taking the three-dimensional body and saying, I'll sort of pre-process it to give me a beam, run the analysis of the beam, post-process it to do the full structural analysis. So that's the sort of approach we're taking.
The other questions related to the action. I think the model, because nobody has done the implementation, or because it's not yet clear how to do it in a OpenFAST kind of framework, like not so expensive.
Say it's both. I'm not sure I fully know how to do it right now myself in an engineering sense. So on CFD, yes, you do two-phase flow and you just solve it. It's expensive, but you could do it. And so NREL has a big project on that. But yeah, it's really for expediency right here is, we have two independent stochastic processes, an aerodynamic one and a hydrodynamic one. And we ignore the coupling, assume that any, big wave will push some wind event. We basically ignore that right now and assume it's negligible. I am curious. I've still been waiting for the answer from the HFM group to say when does that actually matter? I imagine it's only like big sea states with maybe a little turbulence, but that would actually propagate up. Maybe some farm effects. I'm not sure, but yeah, it's a great question. I don't fully know. Right now, I just want to point it out. Like, it is, you can model wind, you can model waves, but it's not really coupled and solved. The structure will respond to both. Otherwise, it's not coupled.
Thanks.
Yep.
I had you have coupled aerodynamic and hydrodynamic, all the structural solvers, like OpenFAST, or CPAC.
Right.
It's not an NREL tool. It's not NREL tools, but it's possible to couple all of OpenFAST structural solvers.
Yeah, SimBack is a great example. If you go buy SimBack, from that company, because it's Dassault systems now. Like, when you buy SimBack, you can basically get the aerodynamic linkage and the hydrodynamic linkage. And in SimBack, there's full three-dimensional objects, usually for the blades and the Tyler still doing beams. But if you wanted to sell with complicated structures, you could do that in SimBack. Yeah.
So, but now when I feel like wave loading cases or where I need to hydrolyze line and everything. So I was just looking for that. Is there any automated scripts that there where we need not go manually and just run the OpenFAST by changing the required things in that script? Like, if I want to change the DLC 1.2 wave loading cases, I want to run. So I just call my the new file which I generated the DLC, which is already integrated with OpenFAST. So just change that file and then run the script. So is there anything available at the time?
Yeah, so I think Emmanuel will touch on this in the next session a bit. There's some scripting ways of doing it. In terms of like the full package, I would say NREL's investing in this WISE framework again. So in WISE is where you define your ISU load cases, and it basically is doing the scripting in the background and it generating all the TerpSim files, generating all the OpenFAST files through the WISE input set. So you don't really touch OpenFAST at that point. Like, it's running OpenFAST, but you don't have to change the files directly. Things, writing the scripts versus a full WISE. I'm not sure you're going to get into full WISE, but at least we'll talk through the options available. I would say, WISE, we have a nice project actually next week is a kickoff meeting for WISE Phase 2, where WISE will become much better, I would say, over time. Right now, it works, it's powerful, but it is a bit user friendly, so user unfriendly. So I apologize about that, but that is coming in the future, improved versions. We are at the break, so I'm gonna pause it there. We'll go for a lunch break. Again, after lunch, we'll stop this presentation, lecturing stuff. We'll get their hands dirty with Emmanuel. And then, yeah, so see you in the back in an hour, and thanks.